All right, so today we have a change of plans. Due to a lack of chemicals, no lab today. So we are going to go over the 3 problems in the book that were assigned, as well as going over the worksheet. And then we'll probably do some practice, again, just to make sure that we're good with especially calculating the concentration of ions in solution. I may just give you one more practice on that. And then depending upon where we are in the day, we may end up starting new material. If I hadn't screwed up and there wasn't any chemical, I knew that we weren't doing a lab and we're doing this today, we'd probably have scheduled a quiz, a test over stoichiometry for tomorrow. But I'm not going to spring that on you one day, so it's going to be Monday. Okay? So that's going to be for regular stoichiometry, grams to grams, mass, mass to moles, moles to mass, limiting reactant, at how much excess reactant, and then molarity, and doing stoichiometry with molarity. Okay. Now we threw in on the worksheet. There's percent yield as well, and I'm going to touch on that. But that's pretty strict, simple concept as well when you're doing a stoichiometry problem, doing the percent yield. So we'll talk about that today as well. Okay. Are we all good with that? So I say quiz. It's going to be a quest, probably a major quiz, small test. 75 points, probably somewhere in that range, because it's going to be a lot of math problems, so I can't give you a whole lot of problems, and so I don't want to make each one worth 15 points, because then if you miss one, you're out the creek. So somewhere along those lines, okay? I'll be a few multiple choice, just talking about mole ratios and balanced equations, and what you can deduce from a balance. A lot of the mole type questions, if you have this many moles of reactant, how many moles of product you're going to get just from the balanced equation, which, that type of multiple choice. All right, so does anybody have any questions about that as far as we're good? All right, let's look at, so 85 and 86 you felt like were okay. 87 gave a lot of people problems. Hopefully 88, if you got 87, 88 then is very, very similar. But we'll look at these on page 161. See if I can. Did I not already go over 85?
I thought you did it.
The 85 we did in class, right?
Yeah.
So I just need to go over 86, 87, 88.
Yeah.
All right. Let's go up just more. Okay, so an 8.65 gram sample of an unknown group 2A metal hydroxide is dissolved in 85 milliliters of water. An acid-base indicator is added and the resulting solution is titrated with 2.5 molar HCl. So when you see the word titrated, that simply means both of these are going to be solutions. They're just mixed together. We did that in chemistry 1. That's where the acid base, you had the phenolphthalein that was colorless in the acid, and then you added the base to it. It turned magenta, pinkish color, and then it went away, and then finally the pink stayed, and hopefully it was just 1 or 2 drops that caused the pink to stay. Does everybody remember doing that? It was with the vinegar. That's a titration. Okay, so you have a known amount of acid, in this case you had vinegar, we added the base to it, and the indicator changed colors. That tells us that the mole ratio is exact at that point. That's the equivalence point. Okay, so just get the terminology. So part of the challenge on these problems is understanding the words. Okay, because it's a whole new language and they're given that. So we see these words. So when the equivalence point has been reached, that just means the reaction's done. Really, you have no limiting reactant at that point. Okay. What is the molar mass of the metal hydroxide? What's the identity? So again, first off, a metal hydroxide. What's the formula going to be for an alkaline metal hydroxide? MOH, right?
Yeah.
But is it, what's the charge gonna be on M?
2.
Plus 2. So it's gonna be, what's the charge on OH? Minus 1. So the formula is gonna be OH2. Okay? So that's the first thing. Now, what's molar mass equal? What units? Grams over mole. Okay? So the question is, what's the molar mass? So, do I know now so in order to know the molar mass, I have to know these two things. In my problem, am I given either one of these two things? I know how many grams I have, right? So it's equal to 8.65 grams of my metal hydroxide over how many moles of the MOH2 I have. So in order to find this is my unknown. I know this must be what I really have to find. Okay? So I can go to a balanced equation, MOH2 plus HCl is going to make what? MCl2 plus H2O. I always say HOH because it's the H plus from the acid combining with the OH minus from the base. It's the exact same thing as H2O, just a different way of writing it, but it shows the positive and the negative a little bit more clearly. Okay, because water doesn't break up or react as a hydrogen and an oxygen. It always reacts as an H plus and an OH minus. Okay, so to balance that, we have to put a 2 and a 2. So now I'm given. So now I say, okay, well, I got to find moles of MOH2. How do I do that? I go back and look. Well, I have 56.9 milliliters of this, and it tells me that it is 2.5 molar. So ultimately, I need to find how many moles of that I have. Okay? So it's important to figure out and write down what am I given, what am I looking for. Okay, because again, the old saying that I made up not too long ago says that if you don't know what you're looking for, you'll probably never find it. If you don't know where you're going, you'll probably never get there. Sometimes even when I'm supposed to know where I'm going with GPS, I still don't get there because I have some directional issues. But that's a different story. So this is my unknown. So how do I go from this information to moles of that? Go ahead, Ann.
Found the moles of the HCl and
Okay, how do we find moles of HCl?
then from the volume and the molarity.
Because molarity times volume always equals moles. Okay? Molarity times volume equals moles. So we can go start with the volume. Now, molarity is what unit?
Moles over liter.
Moles over liters. So we need this in liters, and we can just do this in our head. So this is going to be 0.0569 liters of HCl times 2.5 moles over 1 liter. So you just need to know that capital M really translates the moles per liter. So that gives me moles of HCl. So what's my mole ratio? 1 over 2. So it's 1 mole of MOH2 for every 2 moles of HCl. Okay? So that tends to equals, anyone?
0.07115.
0.071 moles of MOH2. Is that my answer? No. Can you see if I go to here?
Yes.
Okay? So now I come back to this. So my molar mass is equal to my 8.65 grams MOH2 divided by my 0.07115 moles of MOH2. So the molar mass is equal to 122 point,
It's 360.
okay, so 122 grams per mole. Notice units don't cancel here at all, so it's grams per mole, which is what we want molar mass to be. Okay, so that's the answer to A. Now the identity of the metal cation, how do we find, was it this class that I did 85 in, or was it on the video? Okay, and I went, if you watch the video, we got 103, and I said, oh, that's a wrong answer in the book or whatever. But the reality is that that was the molar mass of the whole thing. Think that was an alkaline metal hydroxide. How do we get what cation this is?
You have to like subtract the OH2.
Subtract the OH2. So of our MOH2, that altogether equals 122. So subtract 16 and 1 is 17, times 2 is 34 grams. So minus 34, and that's going to be 12 minus 4 is 8, and 11, 88 grams per mole is equal to M2 plus. And which one is 88? Come over here and you find strontium is 87.62. Okay? So equals strontium 2 plus. Now does the charge matter?
Yes.
As far as writing it, yes, it's making it an ion, but does it affect the mass?
No.
Why not?
These electrons on versus.
Do electrons have mass?
They do,
Yes.
but not very.
It's just so small compared to the rest of the protons and neutrons that we just don't figure it in. So ions and neutral atoms, you use the exact same mass. Okay, so that doesn't change anything. Okay, so just make sure that we're clear on that. We good? Again, what am I given? What am I looking for? Start with the question. Molar mass is grams per mole. I know grams, I have to find moles. Okay? Because part of the problem on these is knowing what do I need to look for. So, we're good there. Let's look at H7. I can do it. My high tech. I know math teachers can write on the whiteboard and do all that. This is my high tech. This is the best I can do. But it works. All right, so a solution of 100 milliliters of 0.2 molar KOH is mixed with a solution of 200 milliliters of 0.150 nickel sulfate. Write a balanced equation. Okay, so it's going to be KOH, and it says solution, so it's going to be aqueous, plus nickel, and it's actually nickel. As if nickels are alkali metal, transition metal. When you look here, it's got a 2 and a 3. What do we need to include in the name? The Roman numeral. Okay? What do we know the charge of sulfate is? Okay, hey, listen, here's the thing too on this one. You don't have to look. The monatomic ions of the halogens are -1. Okay, so Cl minus, Br minus, F minus. Any ion that has even the 8s and the ites, ClO2, ClO3, ClO, they're all going to be -1. These oxygens are all -2. Oxide is O2 minus, sulfide is S2 minus, selenide is Se2 minus. Okay? But even the 8s and the ites, the sulfate, sulfite, they're also going to be 2 minus. Okay? So whatever the base element is, you know, the sulfur, these then are going to be what charge? -3. So the nitrogen family is -3. So except for nitrate, but phosphates 3 minus, arsenates 3 minus, those are the 2 most common in that family. Nitrate's an exception, it's NO3 minus, we're just going to memorize that. Okay, so saying all of that, just to review naming, this is gonna be called nickel 2 with the Roman numeral 2 in parentheses, nickel 2 sulfate. And you know you need a Roman numeral when it's a transition metal with more than one oxidation state. The way you know it has more than one oxidation state, we just look and see if there's more than one number. You do not have to memorize which one's do and don't. Alright, so anyway, you don't need any of that to solve the problem, but that's how we're gonna learn and remember naming. So what do we make? K2SO4. How did you know it was at K2?
Because it's -2 on my SO4.
SO4 is -2 or 2 minus, and potassium is plus. So therefore I know it's gotta be K2SO4 plus, what's the other product?
NiOH2.
Ni, again, we just determined over here that nickel was +2, and the OH is -1, so it's NiOH2. Okay? Now, how would we know what precipitate forms?
Aren't like, wait, oh wait, aren't sulfates always soluble or something?
Not sulfates. What are our three things that are always soluble? Say that
The
again.
alkaline.
Alkali metals, which is going to apply here. All
Ammonium?
ammonium, NH4 plus, and all nitrates, NO3 minus. And it's at the top of the chart there, and it says most cations are all, it doesn't give any precipitates on the right-hand side. Okay? All nitrates, all ammonium compounds, all alkaline metals. Well, potassium's an alkali metal, right? Which means that I automatically know this one's soluble. So if this is aqueous, well, the only one that can be the precipitate is that. Okay? You got it. Those are the only solubility rules you have to know. But you have to know those. And that will be included kind of on the quiz, as far as like, that would be like a multiple choice question. Okay, which of the following, would be insoluble in water, which would be a precipitate, or given the chemical equation, which of the products, would be the precipitate, or which of the substances, I'll probably give you a reactant. So first off, a reactant is never a precipitate. Okay? A precipitate's a product, an insoluble solid that forms during a chemical reaction. All right, so the answer to B is that one. Okay, so C, what is the limiting reactant? So now I go and I look at what's my given. I have 100 milliliters, and that's 0.0 of 0.2 molar, and I have 200 milliliters of 0.150 molar. Okay? So to find limiting reactant, what do we do?
Moles.
Convert to moles and then divide by the smallest one, right? So how do we convert these to moles? Molarity times volume always equals moles. I'm going to just keep saying that over and over until it just rings in your head. Molarity times volume equals moles. So again, this is liters. So I'm going to say 0.1000 liters KOH times 0.2 moles over 1 liter. Okay? So that's going to come out to what, 0.02? If I do my math right? And we should have, that's 4 and that's 3, so 3 sig figs moles of KOH. But we have a coefficient 2, so we're going to divide by 2, but we can do this in our head as well, 0.100. Now this number is nothing. It's just giving us a ratio. 0.2 liters NiSO4, 0.150 moles over 1 liter. Okay, so 0.2 times 2 times 15 is 30, so it's going to be 0.03. NiSO4. And we divide that by 1, so we don't really need to divide it. Okay? So we know, we can see that this is the smaller one than this. So this is my limiting reactant. Okay, so in a multiple choice question is which one of the following is the limiting reactant? Now, just let's state the obvious here. Can either one of these be a limiting reactant? Because we're products, right? They're not reactants. So limiting reactant is limited to these two. But in a multiple choice test, I can give you all 4, and you can eliminate 2 super easy. Okay? So, what does that mean then about my limiting reactant? What do I do with it? So I go now C to D. How many grams of the precipitate are formed? So this is my precipitate, so now I'm looking for how many grams of this. Well, what can I do?
More ratio,
Starting with what?
0.02.
Okay, I always want to use the limiting reactant. I can start right here. Now technically you could start back here and just go liters to moles, but we already know mole. Don't use this one. This one's nothing. You've already divided by 2. So we're going to say 0.0200 moles of KOH times 1 mole NiOH2 for every 2 moles of KOH. This 2 and that 2 are the same 2. Okay? So if you use that number and then divide by 2, you're going to get half the answer that will get what you need. Okay? So always just use the mole value. And then what are we looking for? How many grams? So I need to use the molar mass of this. Does anyone have a calculator?
It's 92.71 grams per mole.
92.71 grams over 1 mole. And all of that equals then
0.927.
oops, this is C. Okay, say that one more time again.
0.927 grams.
So that's your answer to D. 0.927 grams of nickel sulfate form. Nickel hydroxide form. Thank you. You form a product, you don't form a reactant. So that was the part that you guys were fairly comfortable with, but the ones that everybody was asking me then is, okay, well, how do I find the concentration of each ion that remains? Well, let's talk about what's going to be in my beaker when I mix these things together. Okay? So I'm going to put KOH in, and I'm going to put nickel sulfate in. And it's going to make K2SO4. And where is the NiOH2 going to all be? And where?
At the bottom.
At the bottom, because it's the precipitate. So it's just going to be sitting at the bottom. Will any of these ions be in solution? I mean, from the solid? No. Only things that are aqueous are going to have ions in solution. Okay? So, I have that. Now what else? So the nickel sulfate sitting at the bottom is a precipitate. K2SO4 is dissolved floating around in there. Is there anything else floating around in here? The excess. This is our limiting reactant, so we have some of this left over that didn't react because all the KOH ran out. So I still have some nickel sulfate floating around in there. Okay? So that means that none of the sulfate really precipitated out. Law of conservation of mass says whatever, however sulfate we started here, we're going to have the same amount there, right? So, my SO42 minus concentration. Brackets always mean concentration. We can do this one of 2 ways. We can just use this law of conservation of mass. So I know, I've already done the math here. I know that there's this many moles of nickel sulfate because it's 1-to-1, 1 nickel, 1 sulfate, how many moles of sulfate did we originally put into my solution? 0.03, right? So that means that that's how many moles of SO42 minus there were. Now, we could calculate how many moles are in here. Okay, go do the mole ratio from our limiting reactor, calculate moles of this here, and then figure out how many moles of excess we have here and add those two together. But it's going to come out to 0.03 because sulfate didn't go anywhere. It's aqueous here, it's aqueous there. Okay? So, but I need molarity, so how do I get molarity?
Moles divided by liter.
Moles divided by liter. So what's the volume now of this mixture?
300.
300, because we put 100 and 200 together, so we've diluted, so the total volume now of these ions is 0.3. Okay? Which means that this is going to come out to
0.1.
okay? Is it 0.1? Pretty sure.
Yeah.
Yeah, because it's just a tenth smaller than that. Okay? Is that what we got yesterday?
You told us to add the sulfates from both the nickel sulfate.
Well, I did that, but it should have come out, when you added the two, it should have come out to 0.03.
Okay, maybe. I think I did part of it wrong, so that's probably right.
Okay? The other, well, I don't know, we'll see. I'll come back and talk and show you the other way to do this. It's a lot more work. Okay? Now, so we also have potassium sulfate. Okay? So we need to know how many moles of potassium sulfate. Well, it's 2 makes 1, right? And we already kind of figured out that the KOH is this. When you divide by 2, it comes out to this, right? So that means that's how many moles of this that got made. So the K plus concentration is going to equal we'll go 020 moles, I'm going to do the whole thing, moles of KOH, okay, times over 1 times 1 mole of K2SO4 for every 2 moles KOH. Now again, if you just wanted to start at the 0.01, that's fine. I'm just kind of showing how we got there. Then, how many potassiums am I going to get per every K2SO4? 2. Okay? Times 2 moles of K plus for every 1 mole SO4 2 minus. Now, notice these 2's are going to cancel. So the same amount of KOH, again, this is for just like the sulfate, the K's aqueous here, they're aqueous there. So however many moles we have here, we're going to have over there. Okay? Because none of the K's reacted and precipitated out. So, what do we get with this? How many moles? So it's going to equal 0.02. Divided by what? To get the molarity?
0.3.
0.3. So 2/3 is going to equal 0.67. Is that what that's going to come out to? 0.667?
It's 0.0. Right?
Well, just this was a 0.1, so this should be point.
Well, that's a full number.
Oh, that's true. That's true. So 0.067. And we should have 3 sig figs, so 667. So that's the concentration of K plus. So the only other thing that's floating around in there is the excess nickel. So now we have to find the amount of excess, the amount of board space. How much can you see over here?
You can see, like, you can't see that. Yeah, you can see that.
Just to the edge of the white?
Like a little, like maybe an
Yeah.
inch or two.
All right, let's just go, I'm gonna get rid of my picture, we're just gonna go up. Okay? So now my next one I need to find is my nickel concentration. Okay? Well, this is strictly, some of the nickel precipitated out. Some is excess. So to find the amount of nickel, we have to know how much excess in terms of moles. We know how many moles reacted, and so we can kind of do this. So we're going to have to start with 0.02 moles of KOH times 1 mole of nickel sulfate for every 2 moles, and we really already know this one too, but KOH. So this is going to tell me 0.010 moles of NiSO4 reacted, got used, right? Well, how many moles do we have to start with?
0.03.
0.03. So 0.03 moles given minus the 0.0100 moles used. So I have 0.0200 moles NiSO4 excess. Okay? So what do I do with that? So how many moles of nickel do I have then in the solution? 0.02. Because for every one of these that dissolve, I get 1 nickel, 1 sulfate. So my nickel concentration, 0.0200 moles divided by 0.3 liters is going to equal to 0.0667 molar again.
So when we don't know what the solvent is, do we assume that it's water or?
Aqueous automatically means water.
Okay.
And so when it says a solution is mixed with a solution, you always assume that that's water.
And
Okay?
then when both of the compounds are put in the water, do they split up into their ions?
Yeah, they dissociate into ions. That's the only way ionic compounds. Now here's the deep thing. Now I talked about this on the video, but ionic compounds are composed of what type of particles?
Non-metal.
That's the elements that are by, but in what form are they going to be? Ionic compounds are composed of ions. Deep thought, deep right there. Ionic compounds are composed of ions. So NaCl molecule right here is composed of Na plus and Cl minus. So when it goes into water, it doesn't dissolve as an NaCl. It dissolves as an Na plus and a Cl minus. It dissociates into ions. If you remember, you did total and net ionic equations in Chemistry 1. So the only way an ionic compound can dissolve is as ions. So when this dissolves, the K pluses separate from the OH minuses. K pluses are surrounded by water, OH minuses are surrounded by water. That's why, as a solid, it won't react because the ions are held rigidly in place. They can't rearrange, they can't break free. But you put them into water, the water breaks the ions apart, so now they're free to mingle and interact with one another, and so we can get a chemical reaction. Then the nickel and the hydroxide are attracted so strongly to one another, water can't keep them apart. So they form a precipitate. That's what's inside, but the water is not strong enough to break those bonds. If something's soluble, the attraction to the water is greater than the attraction to the individual ions. So we say that they dissociate in water. Only ionic compounds. The next unit we're going to talk about is the solution process and talk about solubility rules and how you know and that a little bit more in detail. But for this, we just know it breaks apart. Dissociates. All right, now, let's talk about the other way to find sulfate. We know that we just said that there's pardon me, it's 0.02 moles, actually one sulfate, of K2SO with, I did it wrong. 0.02 moles of just K plus right here. So I know that I have 0.02 moles of K2SO4 over here, made. We calculated that right here. Started with moles of KOH times 1 mole over 2 moles, okay? So that tells me, oh, actually, we're gonna have 0.01, pardon me. Just 0.02 moles right here, times 1 over 2 tells me how many moles of K2SO4 I have, which is gonna be the 0.01. So that's how much got formed, okay? But I had, of my nickel sulfate, I had 0.03. So how much was excess? 0.02. So you got 0.02 still from here that didn't react. You got 0.01 that did react. So together you're going to have the 0.03 moles of SO4 2 minus still in solution. Because none of it really reacted, so whatever you started with, you're still going to have. So anything that's aqueous here and aqueous here, it's not going to change the concentration. The only one that's going to change is the one that precipitates out. Does that make sense? And so the only one that changed was the nickel. So we found out how much excess we had and then just went from there. Do you want a chance to look at 88 to try to redo it? And see if you can do it 88 now, based upon this, especially 88E. I think that might be a good thing, and I mean, since some of us didn't have a chance to try it anyway. Okay, so those of you at home watching this, so let's go ahead. I know a lot of y'all struggled with 87, calculating these concentrations, okay, of the ions in solution. Try to do, go ahead and pause the video. Try to do number 88. And that's going to take us to the end of first period. I'm going to stop the video now, and then I'm going to start a part 2 when we start the second period.